Hello, welcome to today's lecture on deep learning. After having introduced the attention mechanism, we will today talk about self-attention and positional encoding as two of the most commonly used techniques to implement the attention mechanism in modern deep learning architectures. Say we want to model sequences. The typical way to model sequences is using a recurrent neural network or to use a one-dimensional convolution over the sequence. Today, the goal is to use the attention mechanism to model sequences where we want to feed in a sequence of tokens one by one into an attention mechanism such that each token has its own query, keys, and values. And when then computing the output for a token, it can attend via its query vectors to each other token based on their keys by computing the attention function between our query vector and all the keys of the tokens. Now, the output representation of this function will be a weighted sum over all the other tokens, the values in this case. And because each token is attending to each other token and itself, this architecture is called self-attention. Now, so far we have not told you how we would treat the position in the sequence. We have just talked about using tokens and allowing attention to compare this token to all the other tokens in the sequence. So we will additionally discuss today how we can add other information into the sequence to also take into account the position of the token in the sequence. So formally, we have our input tokens that have a representation vector xi, n of these, so we have x1 through xn. Each one of them has the same dimensionality d, so they are vectors in Rd. And we want to use self-attention to again output a sequence of the same length. So again, y1 through yn in the following way. So for each token with the index I, yi will be computed as a function of the ith token representation xi and of n different key value pairs, where each key value pair is twice the representation of the jth token as a key and the jth token as a value. And how will this be computed? Well, using the standard attention pooling on the database of these n key value pairs and using xi as a query. And that, remember, we will do for all xi's from 1 through n to compute an attention output token for each I from 1 through n. So let's see how this self-attention layer compares to a CNN architecture and a recurrent neural network architecture. So let's start out with a convolutional architecture with a kernel size k. So here on the left we see a CNN with one hidden layer and one output layer. So for a sequence of length n, so 1, 2, and so on up to n, and the identical number of d input channels and output channels, the computational complexity of computing the convolutional layer is O of k times n times d squared. So how does this come about? Well, we have a weight matrix that is size d times d that has k kernel dimensions and is thus k times performing a multiplication of the weight matrix with all of the sequence tokens. This is then slided over the sequence. So each time we have an operation that is k times d squared to compute the output of the kernel at a single location, and we have to slide that all over the sequence. So we have to do that n times to get a computational cost of O of k n d squared. CNNs are hierarchical, so there is only a constant number of sequential operations because all of these operations can be done in parallel. The maximum path length, that is the maximum number of steps that we have to do in order to get from one element of the sequence to another one, would be logarithmic in the length of the sequence. So for example, here we have a sequence of length 5 and we have a kernel size k equals 3. Then in order to have a receptive field that covers two elements of the sequence that are 5 apart from each other, would require 2 steps, so would require 2 layers. So here this node has a receptive field of 3, which is k, and this node has a receptive field of 3. And already in the second layer we will add information from these, which is logarithmic in n, in this case 5. Let's compare this to the recurrent layer. So say we want to compute a recurrent neural network on a sequence. Then in order to update the hidden state of a recurrent neural network involves the multiplication of a weight matrix and a d-dimensional hidden state. So each position would have h1, h2, and so on up to hn. And each of those has d dimensions, and ht plus 1 equals a function of ht. And in order to compute this function, we have to multiply a d by d weight matrix to ht. So that's a quadratic operation. And we have to do that for each of n hidden states, resulting in a total computational complexity of, well, d squared per hidden state, and times that would be O of n d squared to update all the hidden states of the neural network. Now, in contrast to the CNN, this has to be computed sequentially, because here we have a recurrent formula. So we first have to compute ht before we can compute ht plus 1. So we have a total of n sequential operations which cannot be parallelized. So the only thing that can be parallelized is this O of d squared operation that we have to compute for each hidden state. And the maximum path length is O of n, so the number of hops that we need in order to traverse a sequence of length n, in this case to go from x1 through x5, would be n, because we have to go through all of these computations for the hidden states before we arrive here. And finally, let's compare this to self-attention. In this case, we said that we want to use the d-dimensional representation of each xi as queries, keys, and values. So we have n of these. So these would be a matrix X that has n rows, and each of those rows would be x1 transpose up to xn transpose, where each of those little xi's has d dimensions. Now, if we want to compute attention with query equals the matrix X, keys equals the matrix X, and values equals the matrix X, then we have to compute X times X transpose. So an n by d matrix is multiplied by a d by n matrix. We have to then, well, divide that by square root d, then compute the softmax of that, then take the output of that and multiply it by an n by d matrix, which in turn would be X. So the output of this is an n by n matrix, XX transpose, or softmax of XX transpose divided by square root d, and this is again an n by d matrix. Now, what's the cost of that? Well, computing the dot product between an n by d matrix and an n by d matrix transpose, so a d by n matrix, would be an n squared d operation. Then we compute the product between an n by n matrix, which is the result of the product between these two matrices, and multiply it by an n by d matrix. That again is an n squared d operation, so 2 O of n squared d operation, and we can ignore constants, so in total that's an O of n squared d complexity in order to compute all the output tokens. So that would be our matrix Y, which has the n outputs of the respective self-attention of each xi with respect to all the other xi's. In this case, each token is directly connected to any other token via self-attention. Thus, the maximum path length is O of 1 because we can reach in one go each pair of tokens within the sequence. And we don't require any sequential operations because all of this can be computed in parallel. So we have O of 1 sequential operations. So to summarize, both CNNs and self-attention are nice because they allow for a lot of parallel computation. And self-attention has the added advantage that it has the shortest maximum path length, namely one that is constant. So for CNNs, we had a logarithmic in n maximum path length. However, we do have a quadratic in n complexity for self-attention. So if we have very long sequences, so remember n is the number of tokens in our sequence, then self-attention becomes prohibitive. So self-attention is nice because it replaces sequential operations with parallel computation. However, we have so far completely ignored the order of the sequence. So when we compute self-attention, when we basically let each token attend to all the other tokens, we have no information about the order of those tokens or how close they are in the sequence. So if we permuted our sequence, we would actually get exactly the same permutation of the output tokens of self-attention back. But there is a trick, namely positional encoding, that preserves information about the order and the distance within the sequence. These positional encodings that can either be fixed a priori, as we will show in a second, or they can also be learned, so have some trainable parameters that are fit. A simple form of positional encodings is based on trigonometric functions, so on sine and cosine functions. So the nice thing about sine and cosine functions is that they are cyclical. And the trick here is to add a number of features. So if X is our matrix that holds all the d-dimensional representations of all our n sequence tokens, then we create a positional embedding matrix of the same dimension, so n times d, that encodes for each of the n tokens in d features the information about the position. And this information will be encoded via these cyclical sine and cosine functions. So how do these features based on sine and cosine functions look? So for each token that is on position I, we compute d many of these sine and cosine functions. We compute d half sine functions and d half cosine functions. And what we will evaluate them on is based on the position in the sequence. So we will compute a cyclical function and evaluate it at the position I. So here at the row. So that's the position of the token in the sequence. So position 10, we're computing a different number of these sine and cosine functions at the value 10. And as we're increasing the index of the feature, so the column in this matrix P, we are increasing the denominator of the input of this sine or cosine functions, because we're taking a large number, in this case 10,000, to the power of 2j, where 2j is the column, divided by d, the number of dimensions that we're computing. What happens if we increase the denominator? We are reducing the whole input of the sine function, because we are dividing I, the position in the sequence, by a larger and larger number. Thus, we're basically increasing the length scale of the sine function. So the sine function will get drawn apart. Yeah? So let's look at this function here. So for column 6, we're computing one sine function that has a shorter length scale, so that changes quicker than at column 8, which is a sine function with a longer length scale that is drawn apart. And in the next feature, there will be a cosine function with the same length scale. So the column 7 here is a cosine function with the same length scale as the sine function in column 6. So the difference between sine and cosine function is just that they are shifted to each other. So they have the same length scale, but they are shifted from each other. That gives us an encoding here. Now if we go from column 8, we're again computing a sine function, but one that has a larger length scale, and column 9 is then the shifted version of the sine function, namely the cosine function with the same length scale as the green one in column 8. And now if we look at a different position in the sequence, then we get a different positional encoding by getting a different set of these d values. And if we increase, so if we go from position 10 to 20, you see that these values change a lot. However, if we go from 10 to 11, they would only change slightly. So all those values are more similar if you go from one position to the next position, but if you increase the number of positions, the values change a lot. And by changing the length scale, you have the smaller length scales, so those that change very quickly, that are basically uncorrelated between two positions that are further apart, and the ones with a very long length scale that change very slowly, they would still be similar. So that's a way to also incorporate information at different length scales. Here we see a different version of this same matrix that has here the encoding dimensions. So those are the different sine and cosine functions evaluated at different positions in the sequence. Starting from 0, the first element, to n-1, the last element of the sequence. So this is our matrix P with a color encoding from 1 to -1 in light color. So dark values are close to 1 and the white colors are close to -1, the range of these sine and cosine functions. And you can see the first few columns are those very fast changing sine and cosine functions. And as we are increasing the dimension, so the column, of the encoding dimension, we are making those functions slower and slower moving, such that in the end they're basically constant. And you only see these stripes because you either have a sine or a cosine, so they're shifted by a fixed amount. So in this case, the sine would start at 0 and the cosine would start at a value of 1. Once you have computed this matrix P, the way to input it into self-attention is just to add this information to a matrix X. So the output of our positional encoding in this case would be just to take X and add P to X. And instead of just putting X into our self-attention, we add this matrix X plus P into self-attention, and thus not only compare or perform self-attention based on the information that is encoded in X, so the embedding of the tokens, but also based on the information that is in this matrix P, which encodes the positions in the sequence. So let's summarize this lecture on self-attention. So in self-attention, the queries, keys, and values all come from the same representation. So there are some embeddings of our sequence tokens. And in comparison to CNNs and RNNs, they are similar to CNNs in the sense that they allow for a lot of parallel computation. And self-attention even has a shorter maximum path length, which is constant because all the elements of the sequence can attend to all the other elements of the sequence, just using a single self-attention layer. Whereas in CNNs, you have logarithmic path length. The downside of self-attention is that because each token can attend to all the other tokens, this creates a quadratic runtime in the number of tokens, which becomes prohibitively slow for very long sequences. And finally, positional encodings allow to compute features that depend on the position in the sequence, so basically on the index of the respective token, add that to our matrix X to give our self-attention layer not only information about the embedding of this token, but also information about the position of the token. And with this summary, I want to say goodbye and see you next time.